Well, hello to all of you, and hello to all of you on Zoom, and hello to those watching from the future. This is Semester 2, 2022, and this is a revision seminar for Statistics and Numerical Methods, which is a course combining a few bits and pieces for engineering, as separate from the Numerical Methods course that's taught in the Maths degree, which is all numerical methods. This course is a bit of two things. So, taken some requests. This is the second year that this course has run. And I was on long service leave last year. So there's a few things that I have learned this year about some of these things. So the requests I've been given are on the board behind me. You can't see them in the video probably. But I've been asked about test statistics / p-values and about error/big O things with numerical derivatives and integrals and Taylor's theorem stuff. And I have had at least 2 requests from different people about this last thing I mentioned, so I'm going to talk about that first, because that's the thing that several people are worried about. So that's what we're going to start with, and I'll see how I go. I'm going to need your help, because I don't know what's exactly in the notes, slides, whatever, exactly what's in them for this course, because as I said, it's different to the way it used to be. And the way people say things, as you might have discovered if you Google anything in this course, it will look different on the internet than it does in this course. So just need to know how it's done in this course. Okay, so right, bear with me for a second because I do have some examples. All right, so I've been given one here which I reckon is from a quiz or test or something. I should make a heading. That's what I've been asked about. Right. I'm just going to start and say what I think Taylor's theorem says, and then we can line it up with what's in this course. So, the vibe of Taylor's theorem is trying to write all functions as polynomials. That's the idea of it. And the this is the idea of Taylor's theories. It says that given any function, it should be possible to write it like this, as long as it's got enough derivatives and isn't horrible at that point. So this is any function. This is called the center. And this thing is a Taylor series at or around or about C. And that's the idea. So some things are already polynomials, and that's lovely. Most things aren't. And in this, back in Maths 1B, when you first saw, well, most people in this course did Maths 1B, but you might have done a similar thing at another university. But back in Maths 1B, when you first saw Taylor series, you knew what the function f was, and you figured out what this expression was based on that. And when you did that, you discovered that, well, you didn't, they told you, They told you that there is a formula to figure out what these coefficients are. These are coefficients. Okay, so I'm making this up as I go along, so just bear with me. So any function, as long as it's nice, can be rewritten with something like this. And the correct answer for the coefficients is that an is the nth derivative of f at the point c, like the center that we're thinking about, divided by n factorial. That's the correct thing to go in that spot. Right. That's the answer. And what Taylor's theorem says is that if you attempt to do this and stop at some point and don't go forever, then all the missing bits at the end of that dot, dot, dot can all be wrapped up in a single formula, which is his error, Taylor and Lagrange's error formula. Lagrange, was it? I call it that. It's Taylor and Lagrange's error formula. And so the long version is something like and then there's this thing on the end that says how far this thing is from the real function that you're interested in. And this is Taylor's error formula, and it is for some t between the x and the c. Back in Maths 1b, they used the Greek letter psi in this spot. Now they're using t, which is much friendlier and easier to write. So we're all slightly happier. And we still have the truth that an is fn c over n factorial. So the thing is, this is what I would have done if I had put c in that spot instead of t. That's what I would have done to get the next term in the Taylor series. But what Taylor and Lagrange figured out was that if you pick a different number instead of c to go in this spot, then you can get all of the rest wrapped up into this term here. Yep. That's Taylor's theorem as approximately as presented in Maths 1b. And in this course, the main difference between how Taylor's theorem works in this course and how Taylor's theorem works in Maths 1b is that you don't know what the function is. In numerical methods, you don't have a formula for the function. You don't know if it's sine or e to the power of or some ridiculous polynomial. You don't know. All you have are the values of your function at various spots. And so that's a major issue, but we still deal with it as if we knew what the function was. So we call the function f and we sub things into it, and we use that information to figure out stuff about the function. So we imagine that it has a Taylor series even though we can't figure out what it is. That's the difference. So it's easiest to do just with an example. So I'm going to stop there. Would anyone like to say something at this point or ask something? Yes? There's not a formula like that. Oop. Sorry. No, just one moment. I'm going to make sure that my computer didn't die when I did that. Okay. And I'm going to turn this on. There's another formula in that team has, I'm not sure if it's in there. Hold on. I'm just going to read it properly though. That's a specific example that is slightly different to things. So that's just the example. Yeah, that's the one. The one that you've got in the notes there is the one that's going specifically with that example. Pretty sure. I might read it more closely in a minute. Okay, so good. Now I'll do this problem. So this problem said that there is some function. It says fj is the symbol used for f of xj, f dash j is the symbol used for f dashed of xj, f double dash j is the symbol used for f double dashed of xj, where xj are equally spaced points with spacing h, which is the space between xj plus 1 and xj. And we apply Taylor's theorem around the point xj. And then it says minus 5 of fj minus 1 plus 2fj plus 6fj plus 1 is a fj plus b f dash j h plus c of f double dash j h squared plus o of h cubed. This was in, I presume, a quiz or a Mobius because of the way that this was given to me. Is that right?
Yeah. It was in the sample.
I'm just asking the person who sent it to me on Zoom if that was right. It was in the stats test. Okay. So technically, this is not statistics. Yeah. Cool. People are just calling this course stats, which I find hilarious. Sample test for numerical methods, right? So usually, this would be one step of the working in something else, doing this process. But I'm still going to do this problem because it is useful to talk about. So before I do this problem, I'm going to imagine what's going on here. Here is an x-axis, and I have xj and xj plus 1 and xj plus 2 and xj minus 1. These are different points on the x-axis, and we've been told they're h apart. Like that. That's what we've been told. That's what it means to say the xj are equispaced points with spacing h. So this is the first picture in my head. And what we know is that the function value at this point is called fj. And the derivative at this point is called fj dashed. And we don't know what the function does at any other points other than these points. That's the idea that we've got. All we have is a list of x's and y's, or f's. Okay. So there are multiple ways of trying to do this. And I don't really know what to do yet, but I do have I don't know how to get to this. I can't analyze that at the moment, but I can at least think about what's going on here. Okay. So when they say apply Taylor's theorem about the point xj, that means that the point xj is the C that I was talking about. It's the center. And the thing that told me that was the word about. About gives you an idea of being around something. That's the center xj. So what that means is I'm going to use this thing using C as xj, but I'm going to keep the x as just x, because the idea is I'm going to be allowed to sub in different things for x to figure out different things later. There is a whole separate way of doing this, and I will do that as well. So, Taylor for the function f about the center xj says that f of x is a constant term, which we know is f of xj. So just to point out, this AN thing here, when A naught is f of C, this is f dashed of C, this is f dashed of C divided by 2, and then the next one is double dash, triple dash divided by 3 factorial, and so on. So we're going to do that. It's f of xj plus f dashed of xj, because that's the C, times x minus xj, plus f double dashed of xj times x minus xj squared divided by 2, and so on for as long as you need up until you get to the place where you put in the t. And I don't know how long to do that yet. I have to go at least as far as this because this has an f double dashed in it. But I may possibly need to go to the next one after it as well. And I don't know yet how far I'm going to go. So I'm sorry, I'm going to have to leave a gap here somewhere. I'm just going to leave it at this for the moment. And so what that means is that f of xj, well, I'll get xj minus xj and xj minus xj, and this will just turn out to be f of xj, because they'll all be 0. But f of xj plus 1 will be replacing the x with xj plus 1. And so on, however many of them I need. And the thing is, this thing is called fj. And this thing here is called f double dash j, sorry, single dash j. And this is the distance between xj plus 1 and xj, which according to my diagram is h. And this is f double dash 1, 2. And this is h squared. And there might be other stuff later. I should have left a space, sorry. I'm just going to move this down. It won't affect your stuff. I'm definitely going to at least need an error term in here somewhere. Okay, that's what I've got so far. And f of xj minus 1 now this is fj, this is f dash j. This is the journey from xj to xj minus 1. Like xj minus 1 is here, minus xj will be a negative h because it's going the wrong way. Like that number minus that number is h, and so that number minus that number is minus h. Possibly with some other stuff, there's some pluses here that I've probably missed out. Okay. So this thing is called fj minus 1.
That's okay. I've got to study. I'm watching this lecture video in real time.
Fj plus
Thank you,
1.
though. No, that's fine.
And so now if I create this
Thank you.
thing, I'll get something. Let's see what happens. Minus 5 of fj plus 1 is minus 5 of all of these things. So that was here. That's what it is so far. There's some other stuff to deal with. and 2fj, well that's just 2fj. Fj is fj, because we don't use the Taylor's theorem for that one because that's the centre that we're working from. And 6fj, oh, so that was an fj, crap ass. Sorry, I should have done 6 of fj plus 1. So annoyed at myself. So minus 5 of fj minus 1, fj minus 1 is this one. Now that's times minus h, so it'll be a plus 5 now. Just there's a minus h. And minus h squared is h squared. And so if I add all these together, I've got 6 plus 2 minus 5, which is 3. Because 8 minus 5 is 3. And I've got 6 plus 5, which is 11. And I've got 6 on 2 minus 5 on 2, which would be 1 on 2. So that's what that works out to. And that is exactly what they are asking for. How many fj's and how many fj-h's and how many f-jh squareds? 311.5 is what I've got. And so just to actually finish this off properly, I'm going to put in my errors. It's going to be plus f''t on 3 factorial, which is 6, x minus xj cubed. So I got to the second one, and I would write exactly what I would normally do for the next one, but I'll put a t instead of an xj. And then this one's going to have that. That's not an xj. And so I'm going to get triple dash t on 6 times h cubed, because that distance is h. And this one's going to have triple dash, oh yeah, thank you Zoom. Triple dash summer, oh crap, this might not be the same t as the other one. I shall call it t1. And it'll be poo, David, poo. So that will be plus an f triple dashed of t1 on 6 minus h cubed. And so when I do this thing, there's a plus f triple dash t on 6 h cubed, and this one has a minus f triple dash t1 on 6 h cubed. And so I've got f triple dash t minus f triple dash t1 on 6 times h cubed here, and I add them together, and that is a multiple of h cubed, so it's big O of h cubed. Because t and t1 are actually fixed numbers, I just don't know what they are. And so that is what? All right. At this point, it would be useful for someone to say something. Either ask a question or, yep. So this theorem, so just saying, I'm going to repeat that so that it's heard on the recording. Why are the two t's different to each other? This theorem says that if I pick a specific x, then there is a t that goes with that x that makes this work for that x. But because I've used two different x's, I've used xj minus 1 and xj plus 1, which are two different x's, they'll each have their own t. And also, pardon me, this t is between the center and the x I'm thinking of. And so this t here that goes with xj plus 1 is between xj and xj plus 1. And so that t is here in this zone. And this t is between xj minus 1 and xj. And so that t is here. They have to be different because they're in different places. So if you were using xj plus 1 and xj plus 2, it would not be impossible for them to be the same t, but you wouldn't know for sure. Because if you were using xj plus 2 and xj plus 1, the first t's here and the second t's here, so there's more options for what it could be. Right. So I should have called one of them T1 and the other one T2 to distinguish them from the T that we were talking about before. I'm just going to have some water. All right. Well, now I will say, in various tubes and stuff, there was an alternative way of approaching this sort of question. But I don't think it'll work for this one in particular. So this one I think is the way to go for this particular one. Now I've tried very hard to do my what Maths Learning Centre tutor Damien calls bookkeeping, which is arranging things on the page so that you don't lose things along the way. And so I've done, this is the Taylor series, and this is the one that goes with this one, and it's equal to this thing. This is the one that goes with this one, it's equal to this thing. And then I arrange them underneath each other, lining up the FJ dashes and the H's with each other so it's easier to add them together. Yeah. So at the moment, this is just the first step in a lot of the later problems. So if you are given a particular way of approximating the derivative, you would have to do some of these things and then you would go further than this. And so I would like to do another example. Just going to pause so I can look it up. Okay, let's try that again. Fj is f of xj, x to j's are equally spaced with constant grid spacing h. First derivative approximation is this, minus 3fj plus 4fj plus 1 minus fj plus 2 over 2h, and show this is big O of h squared as h goes to 0. So what you do is you can do what I did before if you want. So you can say, well, I can do Taylor approximations around xj. So I could say f of x is f of xj plus f dashed of xj times x minus xj plus f double dashed of xj on 2 times x minus xj squared, and so on forever, up until the point where I put the t in. So I think, my guess, is that the t is going to go here. Because my instinct, based on how these questions go, is that the one with the t is the one that ends up with the h squared, because it's the one that ends up inside the big O. So I reckon that for the purposes of this question, that I should put a t here. For some t between xj and x. That's Taylor's theorem here. Now I don't know for sure, but I'm pretty sure, because the power here that is the power of h that ends up in the big O usually. Okay. And so what that means is that f of xj, which is what fj is, and that's the first thing that appears in this, f of xj is f of xj, and there's nothing I can do about that. The Taylor's theorem doesn't help with that because you need to know f of xj to figure out f of xj. So when I look at this thing, I'm not going to use Taylor's theorem for that, so I need to know f of xj to figure out the other things. So f of xj plus 1 will be f of xj plus f dashed of xj plus xj plus 1 minus xj plus f double dashed of t1 on 2 xj plus 1 minus xj squared for some t1 between xj plus 1 and xj. And based on my diagram, here's xj and here's xj plus 1. That distance is h. That's what this is and this is. And so I get fj plus 1 is fj plus f dash j. Oh, just a second. Wait. We're going to be dividing by h when we do this calculation. And so something that was h squared will become an h. And so something that was h cubed is going to become an h squared. We actually have to go to the third one. Sorry about that. Right, I'm going to have to add that in. So sometimes I have to fix it later. So I'm just thinking, it suddenly occurred to me that if I form this calculation out of these two pieces, there's going to be a piece with an h squared in it, but then I'm going to divide by h, and that'll leave me with an h, not an h squared. So what I need is a piece with an h cubed in it, so that when I divide by the 2h, it comes out to have an h squared. Right, so I'm going to do this instead. Okay, and so what that works out to be is fj and f dash j times h and f double dash j on 2 times h squared and f triple dash of t1 on 6 times h cubed. That's what I get there. Okay, and f of xj plus 2 will be f of xj plus f dashed of xj times xj plus 2 minus xj plus f double dashed of xj on 2 times xj plus 2 minus xj squared plus f triple dashed of some other number x2 on 6 xj plus 2 minus xj cubed. So I've done exactly my Taylor series. I've replaced my x with xj plus 2. And so this is f of j plus 2, this thing. This is fj. This is f dashed j. And this is 2h. Because according to my diagram, this is xj plus 2. That's how far xj plus 2 is from xj. And so xj plus 2 minus xj is 2h. which is fj plus 2 of fj dashed h plus, now 2 squared is 4, but 4 divided by 2 is 2. And we get 8/6, whatever that is, which is 4/3. And so now if I make the thing I want, which was this thing, all right. No, I can do it. I can cope. So the minus 3fj is just minus 3fj. There's nothing I can do about that. But the 4fj plus 1, I know what fj plus 1 is. It was at the top of my page. What was it? F4fj plus 4 lots of f dash j times h plus 4 divided by 2 h squared, so 2 f double dash j h squared, and then 4 divided by 6 is 2/3. So that's what that one works out to when I multiply it by 4. So we had this, and I multiplied each term separately by 4. That's what I did. And then I'm going to minus this thing, which I just made. When I do that, it works out to this. Minus 3 plus 4 minus 1 is 0. There's no fj's. 4 minus 2 is 2. 2 minus 2 is 0, plus this. So now I have this thing here is equal to this thing here. And so the thing I actually want is this divided by 2h. So I'll divide both parts of this equation by 2h, and I'll get minus 3fj plus 4fj plus 1 minus fj plus 2 over 2h is equal to this divided by 2h, which is fj dashed. So there's 2's there, so I'll divide those by 2. And I'll divide this by h. And there you go. This thing works out to be the derivative I want and something of the size h squared. The multiple of h squared. And so that's the error. So this is the approximation, this is the real thing that I want, and this is the error. And so that error is big O of h squared because it's a multiple of h squared. Yay. I will just check something, one moment. So I think it's mostly okay to run with this and just say it's big O h squared at that point, but there is a technical detail that appears in the assignment solutions or the tute solutions that probably wouldn't be the worst thing to mention, which is what you normally do at this point is you say, if the third derivative of your function is bounded on the domain from xj to xj plus 2, then both of these will be less than or equal to that upper bound. So you'll say the error is the absolute value of this thing the absolute value of that. The h squared can come out, and then this is less than or equal to 1/3 of f triple dash t1 plus 2/3 of f triple dash t2. So when you expand an absolute value out across a plus or a minus, it turns it into a less than or equal to and a plus. All the minuses will become plus because we're absolute valuing them. And if f triple dash is always less than or equal to a maximum, if f triple dash of t is always less than or equal to some m, then you can do that. And so then this is equal to m times h cubed squared, which is big O of h squared. Yay. So I don't know if you have to do that bit of the working or if you're allowed to just skip straight to this is big O of h squared here. Not sure, sorry. I don't have enough experience with this course and the people who teach it to know. Maths 1B, fine, do that 3 times a year. But this one, it's only the second time I've seen it, so I don't have instincts for what they want. But this is what's in their solutions. So if you don't mind, I'm going to do an alternative way of doing that, which I saw in one of the other solutions, because it must be allowed to do both of them. So I'm going to run with that too. But before I do that, how are people feeling about what happened there? Yep? Right, I'm going to repeat that question. Why are both this f triple dash t1 and f triple dash t2 both m? So the first thing I'm going to say is they're not actually equal to m, they're just less than or equal to m. And so I'm going to declare that on this zone from, like the T1's in here and the T2's in here. Like the T1's between this one and the T2's in this zone. And so the two of them together are in this zone. And so if I say that whatever the third derivative is, it has a maximum everywhere in this zone, then both of those third derivatives will be less than whatever that maximum is. Really important question, because I went to all this effort to say that T1 and T2 were different and then suddenly they're the same. So I get why that's a problem. But they're not the same, they're just both less than or equal to something. And so whatever they are, they're different, but they're both less than this. Okay, so I just wanted to do an alternative version of this same problem. So an alternative version of the same thing is to do Taylor's theorem, but not on... Oh crap, maybe it doesn't work. Nope, but not on the function f, but on a different function. Okay, so this is the thing that we were trying to show had an error of big O of h squared. what if, so this thing is equal to this, minus 3 of f of xj plus 4 of f of xj plus 1 minus f of xj plus 2 over 2h. That's fine, that's what those things stand for. F of xj plus 1 is f of xj, is xj plus 1 is xj plus h. There's xj plus h is xj plus 1. And this is f of xj plus 2h. And so, if xj is a constant and h is a variable, this is a function of h. Let g of h be this function. And let's do Taylor's theorem for g. At h equals 0. Now, if they had specifically said use Taylor's theorem on f at centre xj, you would have no choice but to do the first working that I did, because that uses Taylor's theorem on f. But if they just said use Taylor's theorem, and they didn't specify what function to do Taylor's theorem on, you could do this. So g of h will be g of 0 plus d dashed of 0 h plus g double dashed of 0 h squared, and so on for as long as I need to go for. And the same thing's going to happen as happened last time. I'm going to make, this is going to be approximated using this thing here. And so I'm going to make, I'm going to use the third derivative to get my h cubed, same as I did before. So I'm ignoring what the xj is doing now and just focusing on the h's. So since h, the centre for h is 0, this will be an h minus 0 here. And this will be an h minus 0 squared, because that's what the centre is. And this will be an h minus 0 cubed. Just to make it completely explicit, I always forget to put the numbers on the bottom. What's going on? Okay. So let me figure out what g of 0 is. G of 0 is minus 3 f of xj plus 4 f of xj plus 0 minus f of xj plus 2 times 0, which is 3f of xj plus 4f of xj minus f of xj, which is 3 plus 4 minus 1 of f of xj, which is 0. So cool. Love this particular way of doing it. And g dashed of h, I differentiate g with respect to h. So this does not involve any h's, so it will disappear when I do the derivative. This will be 4f dashed of xj plus h times the derivative of the inside, which is 1, because that's how many h's there are there. And this is f dashed of xj plus 2h times the derivative of the inside, and which is 2 because there's 2 h's there. I did the chain rule on this thing. Derivative of the outside is f dash, derivative of the inside is 2. And so g dashed of 0 is 4f dashed of xj minus 2f dashed of xj plus 0. And so that is 2f dashed of xj, which is 2f dash j. That's what d dashed of 0 is. G double dashed of h would be the derivative of this with respect to h. So I've got 4f double dashed of xj plus h times the derivative of the inside, which is 1, minus 2f dashed of xj plus 2h times the derivative of the inside, which is 2. And so G double dashed of 0 is 4f double dashed of xj minus 4f double dashed of xj, which is 0. And f triple dash, because that's in my formula as well. So G triple dashed of h is going to be 4f triple dashed of xj plus h minus, and then there's going to be a times another 2 that comes out of this one. So just to be completely explicit about it, okay. And so when I put a t in there, it'll just replace the h's with t's, and there's not much I can do about that. So okay. Doing well. Now, no, deal with that later. Deal with that later. Am I going to deal with it now? I just know that the error is going to have the bit with the t's in it, right? And I'm going to have to do the absolute value of that at some point, and so I'm wondering if I should do it now. And in fact, I don't even need to know that. Oh, I didn't need to do that at all. Not necessary. Not necessary at all. Scratch that completely. No point whatsoever. Yes, okay. Don't do that. Don't need to do that for this one. Okay, let's sub in all the things. Where were we? I just lost my place, just a second. Yep, here it is. This is my g of h. And so I'm going to sub them all in. So g of h was g of 0 plus g dashed of 0 h plus g double dashed of 0 on 2 times h squared plus g triple dashed of t on 6 h cubed. And so g of h is therefore g of 0, which was 0. That was here. Plus g dashed of 0, which was 2 of fj dashed. Plus g double dashed of 0 on 2 times h squared, but g double dashed of 0 was 0. Plus g triple dashed of t on 6 times h cubed. All right. So doing well. And so now I'm going to divide everything by 2, h. So divide that by 2h, I'll divide that by 2h, I'll divide that by 2h, and here we are. And this is exactly this, which was the thing I was trying to use to approximate fj. So just to be absolutely completely clear and explicit, 3fj plus 4fj plus 1 minus fj plus 2 over 2h is fj dashed plus g triple dashed and 12h squared. And as long as this is bounded, we've got a big O. So if G double dash, so the error, the absolute value of the error is the absolute value of G triple dash T on 12 times H squared. So if the absolute value of G triple dash T is less than or equal to M, then the error is less than or equal to M on 12 times H squared, which is big O of H squared. Yay! Both of them are possible ways of dealing with this. Some people feel more comfortable with the other one than the other. The G one requires slightly less fiddling around, but it takes some presence of mind to allow yourself to do such a thing. Yeah. Because this M is the derivative of G, not the derivative of F, so it's a different M. Yeah. So I should have called it N or something. Yeah. And that's why the answers are different. For the recording, I was asked why were there two different answers. Yeah, because the other one was like 2/3 of, it was just M, wasn't it? Yeah, so G is technically a different function. There you go. So, does any, yes? Yes, I'm trying to make it into this original thing here, and only the numerator was G. So G was this bit, and so I'm going to divide by the 2H to make it into this thing. Is that okay? Yeah. And you don't want H's on the denominator if you're going to do Taylor series with center 0, because it doesn't exist when H is 0. So you don't want to do that. So technically you can't make a Taylor series for this, but you can make a Taylor series for this. Which I only just realised why it was done the way it was done. So there you go. So personally I feel more comfortable with the first one than the second one. The second one I love, it's very clever, but I'm not sure I could remember to do it. Yeah. And the first one, if they explicitly told me to use Taylor series on F, then I would have no choice but to do the first one. But I wanted to put them both in because both of them have appeared as solutions in this course, and so it's good to understand how they both work. That is plenty of that, I think. Okay. I have some questions I want to clarify about this course with integration. Hamish, did you want to ask something?
Yeah, I put some questions in the chat.
Oh, and my computer's mute is on. Can you say that again?
I put some questions in the chat if you could answer those when you get the chance.
Oh, that one, okay. Crap of all crap. I'm recording now, and the first word I said after I started recording was crap, but let's go for it. I don't know when I stopped, and I'm so sorry if I missed anything for those who are watching online. Sorry. Damn. Integrals, yay. We have now, through the help of people looking at their notes, discovered that Simpson's rule goes like this. In this course, you start at x1 and go to xn, and not starting at x0. And there have to be an odd number of points for Simpson's rule to work. And the gap between them is h. And then the integral of my function from this point to this point nope, not me. From this point to this point is h on 3, so this distance divided by 3, times the function value here, plus 4 of the function value here, plus 2 of the function value here, plus 4 of the function value here, plus 2 of the function value here, and so on, all the way up to 2 of the second last function value plus 1 of the last one. And that's why you need an odd number of them so that you can do that alternating 4s and 2s. Okay. And then I was saying that all of your integral approximation methods are based on this idea that the average value of a function is its area divided by its width. So you've got this random function. If you go that area divided by the width, it should give you the average value. And what that means is that the area is the average value times the width. So what if you don't know what the function is, and therefore you can't calculate its integral? So to find the average value of a function, why don't you average some of its values? It's my favorite thing. I don't know if the lecturer said any of this stuff. Did they? I don't know. So this is the official meaning of average value, but why not we average some values to figure out the average value? So what I'm going to do is I'm going to cut it into small intervals, and on every one of those intervals I'm going to average some values to figure out what the average value is, and multiply them by the width of the interval, and it should tell me the area on that interval. That's what I'm going to do. So this is now the procedure. Cut into intervals. Average some values in each, and multiply by the widths, and then add them up. And that should be my overall integral. Okay, so when you do the midpoint rule, you decide not to average some values, but just to pick one value as your approximation of the average value. And you go, well, the one in the middle is not the worst. The average value equals f of the midpoint. It's great. When you do the trapezoidal rule, the average value is the left-hand end and the right-hand end divided by 2. It's literally the average of the left end and the right end. And in Simpson's rule, the average value is f of the left end and f of the right end and 4 times f of the middle. And because that's 6 different numbers, well, 4 of them are the same, that's 6 numbers. This one and 4 of those ones and 1 of those ones is 6 numbers total, so we'll divide by 6. Okay, that's an average. So we've just put the one in the middle in 4 times. So just to be absolutely clear, f of left plus f of the middle 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 plus f of the right divided by 6 because there's 6 numbers. Okay. Now you're thinking, of course you are, you're thinking, but why is this a 3, David? Sorry? And that's because you need to use 3 function values to do it. And so your interval is actually 2h wide. And so you have the area on these 2 intervals is f of the left one and 4 of f of the middle one and f of the third one divided by 6 times the width, which is 2h, and then the 2 cancels out with part of the 6 to make a 3. Yay! And the reason why you end up with all those 2's in the middle is because you're doing f of this left and f of that right, but then the left-hand end of the next one is the same as the right-hand end of the previous one, and you get 2 of them. Yeah, and that's why it's 4, 2, 4, 2, 4, 2, 4, 2, because it's it's a certain number of pairs of interval, and it's 1, 4, 1, and then another 1, 4, 1. So what we've actually got is x1, x2, x3, x4, x5, one of these, 4 of these, 1 of these, another 1 of these, and 4 of these, and 1 of these, and another 1 of these, and 4 of these, and 1 of these, and so on. And so that's why it's 1, 4, 2, 4, 2, 4, 1. I don't know if any of that helps, but it helped me. Yeah. And the reason why you chose 4 is because when you do a quadratic, it comes out to the exact correct answer. And it magically also works for cubics to get the exact correct answer because math's magic. So maths isn't magic. I shouldn't say magic when I'm talking about maths, but you know. That's okay. We were allowed to have Ms. Frizzle for science. I'm sure we can have maths magic as well. So I don't know if that helps, but I really liked that way of drawing them together and going, well, it is still an average. It's just an average of 6 things. So when you Google Simpson's rule, sometimes it will say H on 6 here. And what that means is that they're talking about the H spanning across 2 things instead of across 1. So just be careful when you Google any of these things. It'll be slightly different, but that's why some of them say H on 6 and not H on 3, because their H is twice as big as your H. Yeah. All right, stats. So I have a question. This course is new, as I said, but the old version of this course also was half stats. They used to have stats and differential equations, which was called Engineering Maths 2A. So they used to have a course that was half stats and half differential equations, and what they did is they gave you a whole course on differential equations and now you've got stats and numerical methods. So when they taught that course, they used to supply in the exam a list of test statistics and confidence intervals. Do they still do that? So they used to have a formula sheet. You don't know? Sorry? No? You're allowed to bring a page of notes. All fine? All right, well. Okay. That was all good, because if someone had that handy, I would have riffed off of that. So I can't know off the top of my head every stats thing that's in this course, because as I've said, they've made a new course. Oh, well, someone in the chat has hopefully, there's a summary table in the notes. Cool. If anyone had that, I would love to see it. Got someone with printed notes, that'll be awesome. Hamish has helpfully given us a... Yep, that's the one. No, I want the physical one. That's okay, it just makes it fancier. This thing. Oh my, I reckon I could fit it all on if I... It can't all be clear at the same time, I'm sorry. Okay, there's a lot in this table. But it does tell me that we have several different, we have 1, 2, 3, 4, 5, 6, 7, 8 situations in which produce test statistics and p-values. Okay, right. Sorry? I don't think we've ever used it. Okay. I'm sure we did a paired t-test. It's all good. Okay. Right. So I'm just going to talk about this for a second, and I'll get back to the details in a minute. One moment. Come on, you can show me. Yep, gotcha. All right. So I can see several pieces in this table. They mention a context, which is quite enigmatic in some places. They mention a parameter. They mention an estimate. They mention an SE, which stands for standard error, and they mention a reference distribution. How do people feel about those things? Yeah? Yeah, it's been a while. Okay. I'm just going to talk about something and then I'll be able to talk about something. What's that? Yeah, you remember that thing we did long ago? Okay. So, in a statistician's, well, these statisticians' minds, all statistical questions are about parameters. So there is this nebulous thing called a population, which is all things that either do or could possibly exist. The population might not exist yet. So if you were interested in a factory that produced objects like ice cream, then your population will be all ice creams that could possibly be produced. And the things you're interested in are ice creams that have yet to be produced. And over in medicine, they may be interested in babies, but they're actually interested in all babies that could possibly be born. Your population, we talk about it as if it exists really, but it's not. Most of the time, the population doesn't exist yet. So we have to imagine all the things that could be. Okay. But the context of the word population is coming from people thinking about there's the whole of Australian students in universities and then we do a survey on just some of them. That's the idea they're thinking of, but we're actually going to apply it to something a bit more vague and philosophical than that. Okay. And there will be some numbers that describe the population. So I will say that whenever you start thinking about all the things that could possibly be, you're starting to think about probability already. Probability is a comparison between a thing that you want or a thing that you don't want, or a thing that you're thinking about compared to all the things that could have happened. So when you roll a die and you say that the probability of getting a 4 is 1 in 6, that's saying, well, that the 4 compared to all of the things that could possibly happen happens 1/6 of the time. And so a number describing that population is called a parameter, and that number is not technically describing the population, it's describing the population's probability distribution. So a number that describes the population's probability distribution is called a parameter. The word parameter literally means next to measurement. Para means next to or following. It either means next to or following or similar to, and meter means measurement. So it means a measurement that follows the population. That's what it is. But like a paramedic is next to the medics. So anyway, but when a mathematician says parameter, they normally mean You know, in mathematics, there's three kinds of unknowns. There's unknown constants, there's variables, and there's parameters. So a parameter is an unknown, but it's a constant. I don't know what it is, but it doesn't change. It's always the same. So a parameter, you don't know what it is, but it doesn't change, as opposed to a variable which changes, but you don't know what it is either. Okay, so you'll never know the parameter. No one ever knows the parameter. Partly because populations are too big, and partly because populations don't exist yet. Okay, so to a statistician, at least your statisticians, the purpose of statistics is to figure out what parameters are and to answer questions about the parameters. So about parameters. Okay. And there are two kinds of questions you can ask about a parameter. There is a, is it equal to this number? So there's that kind of question. Or there's, what is it? So you would think that this one would be a better question. Because this one just says, is it equal to 4? No. Okay. Like, oh, so if it's not equal to 4, what is it? But it's important to be able to answer both kinds of questions. And the point of a p-value and a test statistic is to answer this question. And the point of a confidence interval is to answer this question. There you go. So the purpose of stats is to answer questions about parameters. And we can either ask the question, is the parameter equal to a specific number? And that's what a p-value is for. And what actually is the parameter? That's what a confidence interval is for. And we answer both of these questions with the same data. Okay. And the reason that table is organized the way it is so that you can choose to either make a p-value or make a confidence interval from this information. Okay. So this parameter they're referring to is the parameter that we're asking questions about, and we'll be able to do some things. Okay. How are we feeling? Cool. All right. But the reason I'm asking this thing is that when you read a question and it asks you a yes or no question about the parameter, you must be looking for a p-value or a test statistic. Because that's what this is. It's a yes or no question. Yeah. All right. So that's the big idea, but there's a little more to it than that, which is I'm going to take some data, collect some data from my population. This is my imagining of the population, which may not exist yet when you collect the data. And then you collect the data, and that's got all these individual objects or situations, all with their own number. And they call this a sample. And so these are just some of the things that could possibly be produced by the population. We never know for sure, but we imagine what the population could have been. And we take that sample and we ask ourselves, based on the information in our sample, is my population parameter equal to a number that I'm thinking of? Or what is it? And you know that you can never know for sure either of the answers to those questions because the population doesn't exist yet. Or if it does, it's too big to measure all of it. So you never know for sure, so all of your answers are probability sorts of answers. It's like, oh, I'm 95% confident that the population parameter is between this number and this number. That's a confidence interval. Or I've got this p-value that says the probability of getting data like mine but worse, if the number really was the number I'm thinking of, is low. Like it's all that, it's all probability. And so we're going to make our decision based on probability. And if the probability of our thing is really, the thing we're thinking of is really low, we're going to go other way around. If the population parameter is a specific number, and if it was that number, if the probability of my sample was really low, I'd go, well, if it really was 10, this sample would be really unlikely, so I don't believe it's 10 after all. It's a proof by contradiction, but with probability, so worse. Okay, so what I have to do is I have to make an argument based on probability, which means I have to know how likely my sample is. And that is hard. And so what I'm going to do is I'm going to calculate one number from my sample. Calculate a number, and this thing is called a test. Wait. A number calculated from a sample is called a statistic. Any number calculated from any sample is called a statistic. We are going to calculate a statistic that will be used to test whether my answer has a yes or no question, whether my question has a yes or no answer. So it's a test statistic. A little bit like in cricket, there is such a thing as a match, and a match is any game, but a test match is used to decide who wins the cup. Same deal. Yay! That's my only sport example ever. So my examples are much more likely to be about like the fairies or My Little Pony or something like that. So, okay. So we calculate a number, and here's my number here, and this thing is called a test statistic. And it's called a test statistic because it's a statistic, because anything calculated from a sample is a statistic, and we're using it to test yes or no, that answer is at this number. Okay, so now we're going to say, it's all about probabilities. We're going to, this is the test statistic I got. I'm going to compare it to all the test statistics that could have happened. Because that's what probability is, comparing the thing you've got to all the things that could have been. And the description of all the things that could have happened is a probability distribution. That's what a probability distribution is. It's a description of all the things that could happen. So we're going to compare this, all test statistics that could have been. And that all statistics that could have been is a distribution. And in this table it's called a reference distribution. Oh, okay. So, lovely. Big problem. If you don't really know about the population, how the hell are you going to know about the reference distribution for the test statistic? What the fuck? But our very clever statisticians over the last 100 years, actually most of these things were invented in the 1920s and 30s. So our very clever statisticians, which were pretty much Gossett and Pearson and Fisher, those three guys, at least one of which was a horrifying racist, but we'll gloss over that. The same Fisher was very clever, but refused to explain anything that he thought was obvious. And the tradition has continued in statistics teaching to this day. No. Anyway. Yes, anyway. Fisher's very clever and he invented some cool stuff and we're going to keep using it. So what they discovered was that if you figure out the correct test statistic, then even if you don't know much about the population, you can make a really good guess at what the distribution of the test statistic is. That was their big innovation for figuring this out. That's the idea behind all of this. Even if you don't know much about the population, you can, and you do the right calculation here, you can get a really good guess at a distribution that you know what it is. And not just that, a distribution that someone has already figured out all the probabilities for and put them into MATLAB. That's what we want. Because I could, if I wanted to, calculate whatever I wanted from this sample. You know, I could find the maximum of the sample and go, what does that mean about the mean? And go, oh, well, I don't know, it doesn't tell me anything. And what is the distribution of the maximum? But if we calculate the right thing, we're good. So that's what this table is saying. If I would like to know about the mean in the situation when I know what the population variance is, which is rare, then if I do the calculation of this minus whatever I think the parameter should be divided by this, then the correct distribution for what that works out to be is a standard normal distribution. If I'm in the situation where I want to know the probability of a specific outcome, my population is just a whole lot of yeses and nos, and I want to know the probability of yes. If I do the calculation of this minus the probability I think it is, divided by that, then the correct distribution is the standard normal distribution. But if I'm in a situation where I don't know the real standard deviation, the real variance of the population, I'll do the sample mean minus the mean that I'm comparing to, divided by this, which has got an S instead of a sigma, and what I have to look up is not the normal distribution, but the n minus 1th t distribution. And there's a different one for each size n. Yeah, and there are more distributions than those two. And in fact, you did some. Was that in this course? Did you do like the Poisson in this course? Yeah. So there are plenty of other distributions. There's only a couple that tend to be used when you're doing test statistics. Mainly because they were designed specially for test statistics. The t distribution was discovered because of doing test statistics. Yeah. No one would think to find a t distribution in the wild. They'd just think it was a normal distribution. They look the same. To the naked eye, they look the same. So that's the idea. And right. And so when a statistician, your statisticians ask you about hypothesis tests, they're very funny about saying, what's the null hypothesis? Define your parameters, blah, 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 because they really think it's about parameters. Even though in practice, statistics, your real research question is not, is the mean 50, or is the difference between these means 0? Your real question is more like, does changing this chemical process make a difference to the outcome? That's what your real research question is. But in order to pitch it as statistics, you have to pitch it as, is the mean different before versus after? That's the idea. Your real research question will be, does this make a difference? And you'll have to say, right, can I make it about means? Or can I make it about proportions? In which case you can do it. So here's my first thing. Your real research question is, does situation A versus B make a difference to the outcome, to the number outcome on average? That situation, that question is your real research question. But the way you have to pitch it for doing statistics is to say that the parameter is the mean in situation A minus the mean in situation B. Mu A is the mean in situation A, and mu B is the mean in situation B. That's how you have to pitch it, in order to do statistics of the kind that you've been taught. So even though the original research question didn't mention means, that's what we have to do. And then you'll say the null hypothesis is that that difference is 0. Let me talk about null hypothesis. There are two answers to this yes or no question. Does it make a difference or does it not make a difference? You have to pick one. Oh yes, please do. Thank you. You have to pick one. And the reason you have to pick one is you're going to calculate some probabilities, and you're not going to be able to calculate probabilities if you don't know what the population parameter is. And so you're going to suppose that the population parameter is a specific number and do some calculations based on that. And because you can't do the probabilities unless you know what this is. So you go, well, I'm going to suppose it's 0 because that matches with the idea that it doesn't make a difference to the mean. That's why you make it. But sometimes your null hypothesis is, if your question is the mean 50 like it says on the box, then the null hypothesis is the mean really is 50. Because you're trying to pick a specific number that your parameter is going to be. So that's the null hypothesis. Whichever one gives you a specific number for the parameter is the null hypothesis. And the alternative is that it's not. So they pitch it directly like this, even though it would be much more natural to call it mu A equals mu B. That's much more natural, but that's not about one number, that's about two numbers. But mu A minus B, mu B is technically one number. And so I can pitch it about that one number. So that's the null hypothesis and the alternative hypothesis. And the test statistic will be T that is the natural way of trying to measure this thing. Well, I'll just do the means in the sample and it should hopefully come out to the same answer. And technically it's minus 0 because that's the answer I think it should come out to, divided by the standard error. The standard error is the thing that goes in this spot. And according to the table, the standard error was something. Was this. Oh crap, sorry. Was this thing. That's what goes in that spot. Where S1 is the standard deviation from the ones in situation A, and S2 is the standard deviation for the ones in situation B, and N1 is how many situation A's you've got, and N2 is how many situation B's you've got. So I could call them A and B if I want. But the table says 1 and 2, but you can call them by whatever names you think is most helpful to you today. So if you've got yes and no, you can call them Y and N. If you've got before and after, you can call them B and A, or 1 or 0 and 1, whatever, doesn't matter. And the reason it's a T is because Gossett, back in 1910, I think, I don't know, sometime between 1819 and 1930, 40 years gap, it's fine, it's my lifetime, sometime in that. No, I didn't live then, that's just I'm 43. So sometime there, he discovered that the correct distribution for this is the T distribution with NA plus NB minus 2 degrees of freedom. So if the null hypothesis is true, then the distribution of T is, and this thing is called degrees of freedom because, don't get me started. I prefer to call it the DF, which is the distribution finder. It says which distribution I'm going to be using. Because there's a list of different T distributions. In my head, they live in a big tower block. and the degrees of freedom is which floor they live on. That's the button in the lift you press to get to their apartment. And the normal distribution lives on the infinitieth floor, like Lord Business in the Lego movie. Told you what my references would be. So what that means is that you'll get your data, you'll calculate this, and you'll look up the number you've got in this distribution to decide whether yours is more likely or less likely. And so you'll go, here's my value of t. These are all possible t's that could have happened, and that's what this distribution is describing. All of these t's and how likely they are, and the ones that where this is higher are more likely than the ones where it's lower, and you'll calculate the probability of being further away from the center than the t you got. And so in MATLAB that will be, just wait. So you want to, MATLAB only gives you the left-hand side of one of these graphs, and so you'll go, is it called CDF in MATLAB? Do you know? And you'll stick your t in here, but you need to make it definitely negative, so you'll absolute value it and put a minus. So if it was already positive, the absolute value won't do anything and the minus will make it minus. If it was already negative, then the absolute value will make it positive and the minus will make it minus. So, and then you'll do, that will give you this bit, and then you'll times it by 2 because you need both of them. Yeah. So your t statistic only turns up when you're doing numerical outcomes, like quantitative officially is the word, but numerical outcomes, and you don't know the real standard deviation for the population. That's when the t appears. So numerical outcome, don't know the true sigma squared, you'll use a t of some sort. But how you calculate that t will be different depending on the situation you're in. So some situations you'll get this SC will have this stuff. If you're only asking about one situation, like it's not A versus B, it's just here I am, what's the mean, then there'll only be half as many things involved. And so you'll get a different degrees of freedom and a different t distribution. But if you have a numerical outcome and you do know the true sigma squared, you'll use a z. And if you have right, so last thing, and I know I was supposed to finish at 1:30, but I'm just going to power through for a couple of minutes. So what if you have does A or B make a difference to not a numerical outcome, but how likely an event is. So that's not a numerical outcome, it's just a word outcome. Thing happens, or thing does not happen. Does a situation A or B make a difference to how often an event happens? So, for example, does before I introduce my new factory machine make a difference to how often a fault happens? Fault, yes or no? Or does male versus everything else make a difference to how often whether someone does volunteer work or not? Like, that's not an engineering example, but whatever. Still systems engineering if you really want to push the boundary. So situation make a difference to how often an event happens. That we have to pitch it in terms of parameters, and the parameter is how often that event happens. And so the parameter is the probability of the event in situation A versus the probability in the event in situation B, where PA is in situation A, or the proportion. It's either probability or the proportion. Proportion means fancy word for percentage, but as a decimal, basically. And PB is in the situation B. And so your, I believe your note's called the two proportions test. And so that's my parameter. How far apart are those two likelihoods? And so then you'll say the null hypothesis is that PA minus PB is 0. And the alternative is that they're not. And the test statistic this time is, so X bar is the notation for the sample mean. P hat is the notation for the sample probability. Because there is no reason, it's just the way it is. So theoretically, you could do a hypothesis test to see if the difference was 0.1 and put 0.1 in this spot here, and it would be fine. And then you have to put a standard error in this spot, which I've forgotten what it is, which is why we have the table. Oh, it's so cool. This is so bad. It's that. So this is the test statistic. We take the estimate that they told me in the table minus the value of the parameter that was mentioned in the null hypothesis divided by the standard error that's in the table. And what they said is that this comes from a normal distribution with mean 0 and standard deviation 1, and the name for that distribution is usually Z. It's a normal distribution with mean 0 and standard deviation 1. And this is a very bad way of remembering. You ready? Ready? Look at that N. Now it's a Z. Can't call it N because N was already used for the sample size. So when Gossett invented the t-test, he called it Z as well, but everyone went, we've already used Z, we have to use something else. So it wasn't called the t-test when he invented it. It didn't have a name. So I just want to point something out. When you're doing proportions, you do a different thing when you're doing a hypothesis test than when you're doing a confidence interval. I know that I said that the confidence interval and the hypothesis test use the same data, and they do. It's just that technical details. If the null hypothesis is true, then these two probabilities are the same. And situation A or situation B doesn't make any difference to what the probability is. That's what the null hypothesis says. And if situation A and situation B doesn't make a difference to the population, to what the probability is, then I don't need to worry about which one is which. And so it's really just one big situation. It's not two groups of individuals, it's one big group of individuals. And so the best estimate for what the real PA or PB is what the proportion is in the whole combined group. So this is the proportion in the combined group. So for example, if PA hat was like 10 out of 50 and PB hat was like 16 out of 47, then P hat would be 26 out of 97. So to what I mean, I'm being very careful here. This is the actual sample size. Don't simplify your fractions down, because the big group is 97 individuals, and there's 26 of them that had the event. That's the idea. So this is not how you add fractions, but it is how you combine percentages. Yeah. So this is 20 events out of 50 samples, and this is 16 events out of 37 samples. And when you combine them together, you've got 26 events out of 97 samples. Yeah. Okay. But suppose you wanted to, this helps, you know, and then you look up then you look up the distribution, which looks like the t distribution, but it's not. It's the infinitieth floor of the t distribution. And you look at your z and you calculate these probabilities, and the combined probability is the p-value. And if your p-value is really small, you declare, I do not believe this null hypothesis. But the official way of saying that is, I reject the null hypothesis. That's the official words. So if this is small, then you reject H0. And if it's large, then do they say retain in this course? Some stats courses are really funny about it. You reject it or you don't reject it. But you don't say the word retain ever, because for some statisticians, that's just evil. It's really hard teaching the Maths Learning Centre because every discipline does statistics in a slightly different way. Usually, you know, solving a quadratic equation, that's the same everywhere. But what to say about a p-value? And so you have to decide what counts as small, and most people count under 0.05 as small. Yeah. He says about the 0.05. Yeah. Most people say under 0.05 is small because Fisher, that's what he used when he first invented hypothesis tests. Some people pick other ones. It's not actually the best way of making decisions, but there aren't really any better ones. Like, it's not the best of all possible ways of making decisions, but it's the best one we've got that uses data. So that answers the question of, is the difference 0? But if you wanted to know, well, if it's not 0, how far apart actually are they? Which is asking the question of, what is this number? And if you want a confidence interval for how far apart they are, so what if you wanted to say, so this is how you feel at this point. You go, all right, so the difference isn't 0. What is it? That's what we're thinking at this point, if our p-value came up as 0.05. And the answer to what is it is a confidence interval. You say, well, it's one of these numbers, somewhere between here and here. And so what you'll do is you'll say the endpoints of a 95% confidence interval would be my P1A hat minus my PB hat. And this is a confidence interval for how far apart they are, plus or minus a critical value of the test statistic. So if you would use t for your test statistic, you'd put a t in this spot for your confidence interval, times the standard error. And when you're using t's, or when you're doing things with means, the standard error is the same as the standard error from making the test statistic. But when you're doing proportions, the standard error is different because reasons. So the thing is, if you've already decided that P1A, PA hat and PB, not PA hat, if you've already decided that the real PA and the real PB are different to each other, you can't go using an estimate that was based on the assumption that they were the same, which is what this joined P hat was. This joined P hat here was based on the assumption that PA and PB were the same. I can't use that because I've already declared that I don't believe that assumption. And so I'm going to have to do something else. And so the SE is now I'm going to make a guess and then I'm going to look it up to see if it's right. This is a good practice for you. You should always make a guess and then look it up. That. Whoops. Yeah, I know there's another revision seminar coming. Okay. So let's compare these two to each other. This is exactly the same as what this would be if I replaced both the PA and the PB by P hat. So if the PA was P hat and the PB was P hat, I could factorize it out and I'd get the same thing. That's a really useful thing for me to make sense of. Makes it easier for me to remember it, because I'd already seen this one and I knew what I had to do. But I'm just going to look it up now to make sure it's the same. Yes, I was right. Okay, the world makes sense again. So, yes. And so in this case, you will get two numbers and your confidence interval will be between them. And it's traditional to say the 95% confidence interval is, and then you'll put the two numbers in these spots and with brackets and a comma, because that's interval notation from Math 1A. Yeah. So, and this Z star has to be chosen to be the Z that would have given you a p-value of exactly 5%. If you did a 90% confidence interval, you need the Z that would have given you a p-value of exactly 10%. Because they really do match up exactly. If you actually ran through all of the possible numbers and did, is the difference 0.1, and the p-value gives you a yes or no, and is the difference 0.3, p-value gives you 0, yes or no, is the difference 0.2, is the difference minus 0.1, is the difference 0.15, and you tried all the different differences that could possibly be, and you colored in all the ones that the p-value said retain, it would be the confidence interval. Except it won't be quite the same for the proportions ones, because the standard errors are slightly different, but it's trying to be the same. Yeah, so if you've found a confidence interval and then someone says, if you did a hypothesis test with this number, what would the answer be? You can just say, oh, that number's in the confidence interval, the answer is retain. You don't have to do any more work. Yeah. So there you go. And that is why we need to think about the yes or no question, because without it, we can't make the confidence interval. Yeah, because officially that's what you're doing. You're working backwards to say, what would the p hat minus pb have been in order to make it reject? What would have been in this spot just here in order to make it retain? And it would have been the one that made this Z star come out to the one that goes with 5% on the outside. So for the 95%, this Z is 1.96. Yeah. Classic. Everyone's supposed to know that number. For the 90%, it's 1.645, but I just have done this a lot. So, yeah. And you can ask MATLAB what that number is. So you can say, I need this combined percentage to be 5%, which means I need 2.5% on both sides, which means I need 97.5% down there. And so I can say the norm, it's usually norm inv, I think. I don't know how they do it in MATLAB. You'd have to look it up. Norm inv of 0.75, and it should give you the right number. Because it's 0.975, sorry, and it should give you the number that goes here. Because you have to tell it what the left-hand side is to get the number you want. Yeah. You could have also done norm inv of 0.025 and minused it, and that would have worked as well. But if I'm judging correctly based on the practice tests, they're going to give you MATLAB code and say, here is a list of possible MATLAB codes. Use the right ones to make your confidence interval. Yeah. And so you'll look at it, and one will be have a T and one will have a norm inv, and you go, oh, right, okay, it's this one. Yep. So they won't ask you to write MATLAB code usually. They'll just ask you to evaluate MATLAB code that's already written. That's how they usually do it in these courses. That's enough of that, I think. However, I will say, questions, thoughts on that? For you in the Zoom as well? .975. Yeah, it's because you have to tell it the area to the left, and the Z star is the one that has 95% in the middle, which means it has 2.5% on either side, which means there's 95% in the middle and 2.5% down the bottom, so 97.5% to the left. Yeah. So you could have argued, I need 95% in the middle, which means there's 5% on the outside, which means there's 2.5% on either side, which means there's 2.5% down the bottom. So I could have done norm inv of 0.025, and that would have come out to a negative number, and so I could have minused it, and that would have made it positive. Both of those are possibilities. And it's because it was a 95% confidence interval. If it was a 90% confidence interval, I would have had 5% on each side, which means I would have had 95% down the bottom. We can talk more about this in a minute. You're feeling uncomfortable about what I said? So norm inv is the thing that does the opposite of the CDF function. The CDF function takes a number and tells you the entire area to the left of that number. So if you get norm CDF of 1.96, it would give you 0.975. So the norm CDF says if you've got a number, it tells you the left-hand side, the area. Norm inv takes the area on the left and gives you the number that goes with it. And so at this spot, the area to the left is 2.5%, which is 0.025. And so norm inv of 0.025 will be whatever number's on the z-axis at that spot just there. And then at this point, norm inv of 0.5 will be 0 because you're halfway. And norm inv at this point, I've already gone through 2.5%, and then the middle is 95% because it's a 95% confidence interval. And so far I'm up to 97.5%. And so the area so far at the point I want is 0.975. And that will come out to the number 1.96. But if I was doing a t distribution, it would have come out to something else entirely. It would have come out to something else entirely that is definitely bigger than 1.96. Like as the t distribution goes up the tower, the critical one for the 95% confidence interval gets smaller and smaller. So, yeah. Like you only have to go up to like floor 50 before it gets being like 1.960000 something. So, yeah. Yeah. So, yeah. And so there's a thing, before they invented the t distribution, they only used the normal distribution, and it worked most of the time anyway, because with a big enough sample size, they're almost the same. Yeah. All right, that's enough. I've got to have at least 5 minutes to breathe before the next one, so I'm going to stop there.